Dear students, in this video I explain rules for the Bode plot. So what are the different rules to complete the Bode plot? I explain in this video. The first one, so already last video I explained the total Bode plot for 10 by s into s plus 2 into s plus 4 can be split into the three parts. First one is Bode plot for 10 and Bode plot for 1 by s and Bode plot for 1 by s plus 2 and Bode plot for 1 by s plus 4. Combined all these four parts, finally we can get the Bode plot for 10 by s into s plus 2 into s plus 4. Like that, I explain the rules. First one, if the given system gain is k, here the k is constant, this k value either positive or negative. For example, if k is equal to 10, otherwise k is equal to 20, otherwise k is equal to 15, otherwise k is equal to minus 10, otherwise k is equal to minus 50, like that. Whatever it may be the k value. The rule for that one is, if the given problem is like this, that means g of s into h of s is equal to k, where k is constant. This means k shift the magnitude plot of mod g of j omega into h of j omega by a distance of 20 log k dB upwards if k greater than 1 and downwards if k less than 1. This constant k value is greater than 1, that means positive value. So the Bode plot, the magnitude plot for this system can be drawn 20 log k up direction, and if k value is less than 1, that means negative value, then we can draw the magnitude plot for this system as downwards at a distance of 20 log k. That means, so total Bode plot for a given system is two plots. One is magnitude plot, second one is phase plot. If you want to complete the total Bode plot for this system, so we can draw the two plots. One is the magnitude plot, second one is phase plot. So this is only the magnitude plot. So magnitude means mod g of j omega into h of j omega. So this is 0 dB line, and initially the total graph can be divided into the number of decays. Here 0.1, 0.2 and so on 1, that means 10 different values will be there in between these two, so that this is one decay and this is another decay 1 to 10, 1, 2, 3, 4, 5 and so on 10. This is another decay, like that. Initially the graph can be divided as decays. So, and identify the gain in dB. 0 dB line, this is the 0 dB line, and up values are plus dB and below values are negatives, minus dBs. So that minus 20, minus 40, minus 50, like that, plus 10, plus 20, plus 30, like that. So here now, if k value is greater than 1, that means k value is positive, so that draw the magnitude line, so above 0 dB line at a distance 20 log k. So this is the line. This solid line is nothing but magnitude plot for 20 log k if k greater than 1. So if k greater than 1, we can draw the magnitude plot where we have to draw above the 0 dB line, that means upwards to the 0 dB line at a distance of 20 log k. So this is the formula. So if, for example, if k value is 10, substitute the k value 10 in this equation, this formula 20 log 10. So the value is plus 20 dB. So that the line drawn at plus 20 dB. So this is the magnitude plot for this function k is equal to 10. For example, if k is equal to 0.1, that means so less than 1. So if k is equal to 0.1 means, so the k value, that is so 20 log 0.1. 20 log 0.1 is nothing but minus 20. So that the magnitude plot drawn at minus 20 dB. So that this is the magnitude plot for k is equal to 0.1. This is the magnitude plot for k is equal to 10. So this is the general formula. If k greater than 1, the magnitude plot drawn at 20 dB k up direction of the 0 dB line, and if k value is less than 1, the magnitude plot drawn at a distance of 20 log k in below of the 0 dB line. That is the first one. So magnitude plot. Now phase plot. So this is the phase plot for the given function g of s into h of s is equal to k. This means that phase plot specifies the remains as it is for any positive value of k. But if k is negative, it always contributes minus 180 degrees to the phase angle plot independent of the frequency. So that if k value is greater than 0, that means k value is positive, it contributes 0 degrees. So if k value is 1, we can draw the phase line at 0 degrees. If k value is 10, also we can draw the line at 0 degrees. So that if k value is greater than 0, the phase plot drawn at 0 degrees line. If k value is less than 0, the phase plot drawn at minus 180 degrees. So this is the phase graph or phase plot for k, the system gain k. Combining of these two is called as Bode plot for the function or the system k. Combining of magnitude and phase plot is nothing but Bode plot. So that the Bode plot for the given system g of s into h of s is equal to k is nothing but if k value is greater than 1, the magnitude plot drawn at 20 log k above the 0 dB line. If k value is less than 1, the magnitude plot drawn at 20 log k below 0 dB line. That is the magnitude plot. Next one, phase plot. If k value is greater than 1, k value is greater than 0, so the phase plot drawn at 0 degrees line. If k value is less than 0, the phase plot drawn at minus 180 degrees line. So this is the total Bode plot for the system gain k. That is the first point. Next, second rule or the second factor. Factor 2. Pole are 0 at origin. So for example, a pole is present at the origin. How can you draw the Bode plot? Pole means a simple pole present at the origin means the function is what is the structure of the function? Single pole. Poles are located at numerator or denominator? Denominator. So simple pole means s value 0. So that simple pole means 1 by s. The function given function g of s into h of s is equal to 1 by s. Like that, it is called as simple pole. So pole are origins at origin. Sorry, pole are zeros at origin. That means s are 1 by s or s square or 1 by s square, like that. If a given function is like that, how can you draw the Bode plot? First one is magnitude plot. So both are required for the Bode plot, magnitude as well as phase plot. Initially we can draw the magnitude plot. So this is the formula for drawing the magnitude plot for a pole. Therefore, so magnitude plot for p poles at the origin. So initially we can discuss about the poles after we go for the zeros. P poles at the origin gives a family of lines passing through the intersection of omega is equal to 1 and 0 dB line having the slope minus 20 into p dB for decay. It's very important. dB for decay minus 20. So that the gain decreases minus 20 per decay. For 10 different values, the gain will be decreased minus 20 into p, where p depends on the number of poles. If only single pole at origin, p value is 1. If 2 poles at origin, p value is 2. If 3 poles at origin, p value is 3. So now how can you draw the magnitude plot? So initially taken the graph. So decide decays. Omega is equal to 0.1 and so on 1. This is 1 decay. 1 to 10. This is second decay. 10 to 100. That is third decay and so on. Now, so this is the condition, minus 20 into p dB for decay, and all the lines are intersectioning of omega is equal to 1 and 0 dB line. So that this is 0 dB line. All the curves are intersecting this 0 dB line at omega is equal to 1. So that these are the omega values, 0.1, 1, 10, like this. This is frequency. Frequency in the sense omega. So that all the graphs are intersecting 0 dB line, this line, 0 dB line at omega is equal to 1. That is the condition. And slopes, how can you draw the slope? Minus 20 into p dB for decay. So that, for example, if single pole at origin, p value is 1, that means the dB is minus 20 into 1, minus 20 dB for decay. So that this is the line. So started here. Why? Because so at omega is equal to 1, the curve intersecting 0 dB line. So and the condition is minus 20 dB for decay. So that start at 20 and decrease 20 dB for decay. So 20 and decreasing 20 means 20 minus 20 is nothing but 0. So that 0 dB line intersecting, and again next decay, again minus 20 dB for decay. So that here 0 minus 20 minus 20. So that the line drawn to the minus 20. That means single pole. If another decay is there, so for that decay, here the starts minus 20 and again minus 20 decreases, minus 40 and so on like that. If two poles are there at origin, p value is 2. So that minus 20 into 2 minus 40 dB for decay. So how can you gain, how the gain decreases for decay now? 40 dB decay. So because p value is 2, minus 20 into 2 is nothing but minus 40. So that, so and the condition intersecting the 0 dB line at omega is equal to 1. So where we have to start? At 40 we can start, then only 40 minus 40 0. So that, so start at 40, one decay you want to decrease minus 40 dB, so that 0, and another decay we want to decrease again minus 40, so that the line drawn from 0 dB to minus 40 dB. For example, next dB is there, so for that decay, next decay is there, for that decay, so minus 42, where we have to draw minus 40, again minus 40, minus 80 and so on. For example, 3 number of poles at origin, so p value is 3, therefore minus 20 into 3, that means 60. So now how much gain will be decreasing for decay? Minus 60 dB decreasing for decay, and the condition is that omega is equal to 1 intersecting with 0 dB line. So how can you, how much, where we have to start this one? At 60 dB. So 60 dB and decayed minus 60 for decay. So that 60 minus 60, 0. So that line drawn like this, and again 0 to again minus 60, line drawn like this. Again, for example, one more decay is there, start here minus 60 and minus 60 minus 60 minus 120 degrees, sorry, minus 120 dB, like that the line will be drawn. So this is the magnitude plot for poles, simple poles at origin. If one pole is there, minus 20 dB for decay decreasing. If two poles are there, minus 40 dB decreasing for decay. 3 poles are there, minus 60 dB decreasing for decay, and all the lines are intersecting at 0 dB line at omega is equal to 1. That is the rule if simple pole is there. So this is the magnitude plot for simple pole, and phase plot for simple pole we can run. So this is the, so magnitude, again magnitude plot for zeros. So after completing of poles and zeros magnitude plot, directly we can go for the phase plot for poles and zeros. So this is the magnitude plot for zeros. So here the quite different is there. So each zero at the origin increases the magnitude at a rate of plus 20 dB for decay. Here also the magnitude plots all the curves are intersecting at omega is equal to 1, where this is the line omega is equal to 1 and 0 dB line. So all the curves are intersecting 0 dB line at omega is equal to 1. So if poles are there, so this is the formula minus 20 into P. If zeros are there, this is the formula minus 20 dB for decay for simple or single zero. If two zeros are there, so minus 20 into 2, sorry, plus 20 into 2. If 3 are there, plus 20 into 3. So only the different here minus 20, here plus 20, remaining all are same. So that if only simple zero is there, one single zero is there, so that it will be increasing 20 dB, plus 20 dB. So here plus 20 dB means increasing, and at omega is equal to 1, we want to intersecting the 0 dB line. So that where we have to start minus 20, at minus 20 we can start increasing the 20 dB for decay, it will be reaches to the 0 dB. So that starts at minus 20 and increasing 20 dB for decay and reach to the 0 dB line at omega is equal to 1, and again increase the 20 dB for next decay that reaches to the plus 20. If another decay is there, again increase the 20 dB for decay. That means from 20 to 40, next 40 to 80, 80 to 100, 100 to 120, like that. Next, two poles are there, sorry, two zeros are there at origin, that is s square. That means 2 into 20, 40, plus 40 dB for decay, and at omega is equal to 1, we want intersecting 0 dB line. So that where we have to start minus 40, at minus 40 we can start, so increasing 40 dB for decay, then it will be reaches to 0 at omega is equal to 1, and next decay 0 to plus 40, and next decay plus 40 to plus 80, and the next decay plus 80 to plus 120, like that. So increasing 40 dB for decay. If 3 zeros will be there, then how can you draw? So 20 into 3, that is plus 60 dB for decay. So where we have to start minus 60 dB, we can start increasing 60 dB for decay, and it will be reaches omega is equal to 1 at 0 dB, and for this decay 0 to plus 60, and next decay plus 60 to plus 120, and the next decay plus 120 to plus 180, like that we can draw. So this is the magnitude plot for simple zeros at origin. So here we can simply, how can you remember this poles and zeros magnitude plot? So here this is the magnitude plot for pole, where we have to start from upside and drawn towards the downside. That means, so for example, consider this is the horizontal line, poles are located in denominator and zeros are located in numerator. If you want to write the magnitude plot for, if you want to draw the magnitude plot for poles, so that the lines drawn towards the poles, where we have to locate the poles in denominator only, the poles will be there, in numerator zeros will be there. So that consider this 0 dB line as divided by line, that is horizontal line. Below this line poles will be there, above this line zeros will be there. So if you want to draw the magnitude plot for poles, that magnitude plot drawn towards the poles, that means upside to downward, upward to downward. And zeros, for zeros, so again consider this 0 dB line is horizontal line, and zeros are located at upside, poles are located in denominator side, below side. So that, so start here and move towards the upside. So this is the simple technique to remember magnitude plots for poles and zeros. So where we have to start and what direction we have to draw the magnitude plot, it is very simple to remember. So if you draw the magnitude plot for poles, we can draw the lines from upward to downward. If you want to draw the magnitude plot for zeros, draw the magnitude lines or magnitude plot from downward to upward. So this is the simple technique. So magnitude plots are completed. Now, so phase plots for poles and zeros. So this is the phase plot for poles and zeros. In generally, P number of poles at origin contributes minus 90 into P angle. Overall phase angle plots. This contributes in constant irrespective of the omega. And in generally, P number of zeros at origin, the total angle contributes is plus 90 into P. So this is minus 90 into P. This is plus 90 into P. So if single pole is there, so minus 90 into 1, minus 90 degrees, it will contribute the minus 90 degrees, so that the straight line drawn at minus 90 degrees. If two poles is there at origin, minus 90 into 2, it will contribute minus 180 degrees, so that the line drawn at minus 180 degrees, so that this line for one pole, this line for two poles, and if three poles is there, 90 into 3, like that we can draw the lines. And poles number of zeros is there. If one zero is there, it will contribute plus 90 degrees, so that line drawn at plus 90 degrees if single zero is there. If two zeros is there, plus 90 into 2, that is plus 180 degrees, so that plus 180 degrees we can draw the line at plus 180 degrees. So this is the phase plot for two zeros at origin, like that we can draw. So here also 0 degrees line is horizontal line and reference line. Above this 0 dB, the degrees are positives. Below this 0 degrees line, the degrees are negatives. So here the condition is irrespective of omega, whatever it may be the omega value, the angle contribution is here plus 90, here plus 180. So that if omega is equal to 0.1, the phase is 90 degrees. Omega is equal to 1 also, phase is 90 degrees. Omega is equal to 10 also, phase is 90 degrees, and so on. Whatever it may be the omega value, if 0 is there, the phase plot is minus 90 degrees. So we can draw the straight line at minus 190 degrees, whatever it may be the omega value. That is the condition. Remaining all are same. So that if the number of poles at origin, the phase plot is like this. So plus minus 90, minus 180, like this. Here also we can easily remember, this is the reference line. Below the reference line, poles are there. Above the reference line, zeros are there. So both are 90 only. This is minus 90, this is plus 90. Only the plus and minus is the difference. Remaining all are same. So that 0 dB line. So this reference 0 dB line, above the 0 dB line, zeros will be there. Below the reference line, poles will be there. If single pole 90, two poles 180, three poles 90 into 3, like that we can multiply. So this is the simple technique to remember. So where we have to draw the phase plot for simple poles and simple zeros. So up to now we completed the two factors. First factor is constant K. Second factor is simple poles and simple zeros at origin. For these two factors we can complete the Bode plot. So Bode plot means the combination of two plots, magnitude as well as phase plot. So if you want to complete the magnitude and phase plot, then only the Bode plot will be completed for a given function. So next one, so simple pole and simple zero. That means, so other than origin, a pole is there, other than origin, a zero is there. Then how can you draw the Bode plot for these functions?